All right, let's get into it. Today, we're breaking down the very stuff that makes up, well, everything. We're talking about matter, what it is, how we sort it, and why knowing the difference between a glass of salt water and a bar of pure gold is the key to creating everything from brand new medicines to the materials we use to build spaceships. So, yeah, let's dive in. I mean, it's the big question, right? You look around, the air, the desk you're sitting at, the phone in your hand, it's all just stuff. But how in the world do you even begin to make sense of it all? How do scientists take this infinite variety of things and start putting them into buckets? Well, it turns out there's a system for that, a really elegant logic that underpins pretty much all of reality. And this is our map for today. Don't think of it as just a chart. Think of it as a decision tree. It's how we take all the chaos of the universe and start to bring some order to it. And that very first choice we have to make, that first fork in the road, is probably the most important one of all. So right at the top of our map, we have to ask, is what we're looking at a mixture or is it a pure substance? Now, I know that sounds super basic, but trust me, this one single distinction changes everything about a material. Its properties, how stable it is, and what it's going to take to break it down. Everything flows from this one big question. So what's the real difference here? Honestly, it all comes down to commitment. In a mixture, all the parts are just kind of hanging out together. You know, like a salad. The lettuce and the tomatoes are in the same bowl, but a piece of lettuce is still lettuce and a tomato is still a tomato. But pure substances? Oh, their components are chemically married. Their atoms have actually bonded to create a totally new substance with its own unique identity. Okay, so let's follow that left path on our map for a minute. Let's say we figured out we're dealing with a mixture, just a physical jumble of different things. How can we sort that jumble out even more? And this is where it gets really interesting, because not all mixtures look the same. On the left, you've got a homogeneous mixture, like salt dissolved in water. To your eye, it looks like one single thing, right? That's because the salt particles are spread out perfectly evenly. But on the right, you've got sand and water, a heterogeneous mixture, and you can literally see the different parts. One is blended perfectly, the other is clearly just stuff in other stuff. Which leads to a pretty practical question, right? If the parts of a mixture aren't chemically stuck together, we should be able to separate them just by using their physical traits, without some big chemical reaction. And yeah, absolutely, we've got some really clever ways to do just that. So let's go back to that sandy water. The easiest way to separate them is filtration. And the whole idea is built on one simple fact. Sand doesn't dissolve, and the grains of sand are physically way bigger than the water molecules. That size difference is all we need to sort them out. And here you see it happening. You pour the mixture through the filter paper, the tiny water molecules slip right through the pores, but the big old sand particles, they get stuck. It's a beautifully simple mechanical process. But what if you have a mix of two solids and they're about the same size? Filtration isn't going to work. So we have to look for a different physical property to take advantage of. Like, for instance, what if one of the things in your mix reacts to a magnet? Well, that gives us a completely different, and let's be honest, a very cool tool to play with. Would you look at that? You just take a simple magnet, wave it over a mixture of iron filings and sulfur powder, and it just lifts the iron right out. The sulfur gets left behind. No complicated chemistry, no filters, just using a basic force of nature. It's a perfect example of using a unique physical property to sort things out. Okay, so we've handled the jumbles. Let's go back to our roadmap and take that other path. Now we are entering the world of pure substances, the fundamental chemical building blocks that all those mixtures are made of. And just like with mixtures, pure substances also have two categories. Over on the left, we've got an element, in this case, oxygen. See how it's made of only one type of atom? It's perfectly symmetrical. But then on the right, we have a compound, water. See that structure? It's built from two different kinds of atoms, hydrogen and oxygen, and they're locked together in a very specific way. The most important thing to get about an element is that this is as simple as it gets. Think of elements like the individual Lego bricks of the universe. You can't break down a single red Lego brick into something simpler than, well, a red Lego brick. It's the ultimate pure ingredient. Gold is just gold, oxygen is just oxygen. So a compound is what you get when you start building with those Lego bricks. You take different elements, say hydrogen and oxygen, and you chemically snap them together following a really strict blueprint. Water is always H2O. 2 hydrogen atoms for every 1 oxygen atom. That fixed recipe is what makes it a compound. And remember those easy physical methods we use for mixtures like filters and magnets? Totally useless here. Because the atoms in a compound are chemically bonded, you need to use chemical force to break them apart. Here you can see a process called electrolysis, which uses electricity to literally rip those bonds apart, splitting water back into hydrogen and oxygen. It takes a whole lot of energy to undo that chemical marriage. So we have our categories, right? Mixtures and the pure substances they're made of, elements and compounds. But why does any of this matter outside of a chemistry class? Because this whole system is the key to understanding a substance's properties, and those properties are what determine what we can do with it in the real world. And we look at those properties through two main lenses. Physical properties are the things you can see or measure without changing what the substance is. Its color, how dense it is, when it melts. Chemical properties, on the other hand, describe how it behaves in a chemical reaction, like the fact that iron has a tendency to rust or that wood is flammable. Let's just zoom in on one really important physical property, density. All that means is how much stuff is crammed into a certain amount of space. And this one little property has a huge, visible effect on how things interact with each other. And this is the perfect everyday example. Iron is way more dense than water, so it just sinks. No surprise there. But cork, with all that air trapped inside it, is way less dense than water, so it floats right on top. Simple, right? It's a basic principle that you see in action all the time. And this isn't just about things in water. A helium balloon floats for the exact same reason a cork does. The helium gas inside the balloon is a lot less dense than the air around it. So we take advantage of that simple physical property to make things fly. It's pretty cool. In this slide, this is where it all comes together. This is why all that sorting matters. We don't make cooking pans out of pure iron because of its chemical property to rust. No, we make an alloy, stainless steel, specifically because it resists rusting. We build fighter jets out of special alloys because they're strong but also lightweight. And our entire digital world, it's built on the unique electrical properties of silicon. We choose, and sometimes we even create, the perfect material for the job, all based on its properties. So let's wrap this all up. All the stuff in the universe fits into this logical system. It's either a mixture or a pure substance. We can pull mixtures apart using their physical traits, and the pure stuff, the elements and compounds, are the basic building blocks of everything. And most importantly, understanding a substance's properties is how we build our modern world. When you think about it this way, the whole world is just one giant chemistry set. And by understanding how to sort, separate, and combine all these little building blocks based on their properties, we've gone from the Stone Age to the Space Age. The more we learn about all this stuff around us, the more incredible things we're going to be able to do with it. So yeah, keep asking questions.